नमस्कार बच्चों, मेरा नाम धन्या और हम लोग ग्रेड 11 केमिस्ट्री का लेसन 4 सीख रहे हैं जिसका नाम है केमिकल बॉन्डिंग एंड मॉलिक्यूलर स्ट्रक्चर. So in today's lesson we will be learning about Fajans rule. Okay, so we already discussed before that no bond is completely ionic or covalent. For example, even if it is an ionic bond, it is not 100% ionic. There will be some amount of covalent character in this bond. Okay, so even if it's a covalent bond, there will be some amount of ionic character. So Fajans rule is to calculate the covalent character in ionic bond. So Fajans rule tells us the covalent character in an ionic bond. In an ionic bond, because no bond is 100% ionic or 100% covalence. There will be some amount of covalent character in the ionic bond and vice versa. Okay, so you know that ionic bond is formed by what? Formed by the complete transfer of electrons from the metals to the complete transfer of electrons from the metals to non-metals. So the first, initially there is transfer of electrons from metals to non-metals. And then it appears that there is some amount of sharing going on between the metal and non-metal, and they behave similar to covalent bond. Okay, so for example, if I take sodium chloride, potassium chloride, both are ionic compound formed by metal and non-metal, formed by the transfer of electrons from metal to a non-metal. But Fajans rule tells us the amount of or the covalent character in ionic bond. Covalent character in ionic bond. Okay, so here the question, here two compounds can be given and they can ask you which is more covalent or which is more ionic, which compound shows more covalent character. Okay, they can also ask you which of these compounds have more, or which of these compounds have more melting point. So whichever compound has more of covalent character, that will have a lesser melting point and boiling point compared to the other one. They can also similarly ask you, they can give you two compounds and they can ask you which one has less solubility. So unless you know which compound has more covalent character, you cannot decide these. Okay, so Fajans rule tells us the covalent character in ionic bond. Okay, suppose if suppose compound A and compound B. Okay, if compound A has more covalent character, a compound B has less covalent character comparatively. See, we are comparing it. We cannot tell the percentage, but we are comparing it, comparing B from A or B from A. Okay, so if B has less covalent character, so if we compare A and B, A has more covalent character. A is an ionic bond, B also is an ionic bond, but A has more covalent character. That means it will have low melting and boiling point. Okay, so covalent compounds have low melting and boiling point, and also it will have low solubility in water. Okay, so that is why this Fajans rule. Knowing Fajans rule is very important. The criteria to decide which has more covalent character. Okay, these type of questions they usually they ask in the competitive exam. Okay, so let's move on to the Fajans rule. But before we move on, there is one limitation. As I told you, there is one limitation for Fajans rule. The limitation is that it's a qualitative quantity. It's a qualitative quantity. That means we can just compare two compounds A and B. We cannot say how much percentage of covalent character is there. No, we can just compare A is more covalent than B or vice versa. Okay, so that is why it's a qualitative quantity, but we will get an idea which is more covalent, which ionic compound is more covalent than the other. Okay, so only comparison is possible, right? Now let's move on to Fajans rule. So Fajans rule tells us the amount of ionic character covalent character in ionic bond. Okay, in ionic bond. So that is the objective of today's lesson, Fajans rule. Okay, now suppose I have a cation and an anion. This is an anion. Anion also has a positive charge. So this is cation. Cation is always smaller. This is anion. Anions are usually bigger. Okay, now here there are electrons of the anion. Okay. Okay, so it so happens that this cation, the positive charge of the cation or the nucleus of the cation, attracts the electrons of the anions. They will attract the electrons of the anion, and it appears that the negative charge is concentrated at one corner of the anion. Okay, and the spherical shape of the anion, this is this anion, okay, the spherical shape of the anion distorts and the spherical shape of the anion distorts so these are the electrons of the anion that is attracted by the cation. So this is the cation and it appears, this is the anion. The spherical shape of the anion distorts and gets deformed like this. Okay, so the electron cloud, it's an electron cloud. Electron is a wave, you know, it moves around as a wave around the nucleus, and this spherical shape of the anion gets deformed because of the cation. Why? Because the cation is attracting the electrons of the anion and it appears that the negative charge is concentrated at one corner. And this is called as polarization. This is called as polarization. Here there is more charge here, more charge. So here there is more negative charge. So as if a pole is being formed for anion. Here there's a negative pole. So here there is deficient. So less negative charge. So there is a distortion or deformation of the anion going on. And this is called as polarization of anion. The electron cloud of anion is distorted or deformed. See, initially it was like this, the spherical shape, but now it has deformed. It is more attracted, the electrons seem to be more attracted towards the cation. Now, this electron is for the anion as well as the cation. It appears as if sharing of electron is happening. Sharing is not happening, but it appears as sharing is happening. Okay, so sharing means what kind of bond? So not a bond is being formed, but a certain bit of covalent character comes in. Okay, so looks like as if there is sharing of electrons and there is a certain amount of covalent character that is coming to play. So I'll just show you with a picture. I'll just share the screen for the PowerPoint. So as you can see in the PowerPoint, over here, we have the cation, which is smaller, and the anion, which is bigger. So the electron cloud, outermost electron cloud, is attracted by whom? By the cation, and you can see the electron cloud is distorted. So the spherical shape of the cation is seen to be distorted, and it appears that there is sharing of electron by it appears, okay, it appears a sort of sharing between cation and anion, and there is development of the poles, okay, and this is called as polarization, or this deformation of electron cloud is called as polarization of anion. And there is a certain bit of covalent character that comes into play. Okay, so this leads to the covalent character in ionic bond. This deformation of electron cloud by whom? This deformation of electron cloud by the cation. Because of which, who gets polarized? The anion gets polarized. And because of this, what happens? There is some amount of covalent character in that ionic bond. And this happens in all the ionic compound. Okay? Now, moving on further. Moving on further, when the electron cloud is distorted, it is called the polarization of anion. Similarly, we also have polarizing power of cation. So now this particular ionic bond has acquired some covalent character. Polarization of anion has taken place. That means the electron cloud has got deformed by the cation. Because of what power? Polarizing power of cation. Capacity to attract the electron pair or the electrons. Capacity to attract the electrons. Okay. So this is how covalent character comes into play in the ionic bonds. Why? Because the cations attracts the electrons of the anion, and because of which the electron cloud gets deformed, and this is called as polarization of anion. By whom? By the cation. And what is that called when the electrons are attracted by the cation? Polarizing power, because it is making the anion to form. It is making the anion to get polarized. Okay, polarization is nothing but the electron cloud is deformed. There is formation of poles. Okay, it appears that the negative charge is concentrated at one corner than the other. Right. So in this kind of bonds, or in this ionic bond, there is certain bit of covalent character. Now, how much of the covalent character? So we said we cannot measure the percentages. We can just have a comparative analysis between two compounds or three compounds. Okay. So next question is, or next topic is, how much covalent character comes into play? Covalent character. Now that depends upon two factors. One is polarization. That depends on polarization of anion and polarizing power of cation. Okay, so how much covalent character the ionic bond gets depends upon two factors: polarization of anion, how much it has got polarized, and polarizing power of the cation. Okay, so more the polarization of anion, more is the covalent character. More is the covalent character. I'll denote as CC, short form. Okay. So more is the covalent character. More polarizing power of the cation, more is the covalent character. Okay. I hope till here it is clear. So how much is the polarizing character? We cannot measure the percentage, as I told you. We can just compare between few compounds. Okay. But it depends upon polarization of the anion, which is more. If it is more polarized, more is the covalent character. And also depends upon the polarizing power of the cation. If polarizing power is more is the covalent character. Okay, I hope till here it is clear. Okay, so what is polarizing? What is how covalent character comes into play in ionic bonds? Okay. So students, this is the Fajans rule. Okay, so how much of the covalent character is there in the ionic bond is determined by the polarization of the anion. If it is more, covalent character is more. Polarizing power of cation, if it is more covalent character. Okay, now let's discuss some factors on which this polarization or this amount of covalent character in ionic bond depends. Okay, so how do we determine which one is more covalent, or which compound has more covalent character than the other? Let's find out. Okay, let's talk about cation first. Okay, so for cation, what is important? Polarizing power. More the polarizing power, more is the covalent character. So I'll denote it with PP, polarizing power. Okay, so first one, we go with size. Okay, size of cation. So size of cation. Suppose I have three cations, A, B, and C. And okay, so here, if the size is small, if the size of cation is small, okay, like the atom C, okay, or the cation C, sorry, cation C, if it is smaller in size, all the positive charges or the charge is concentrated in a very small area, and it will be able to attract the electrons more strongly. Okay. But in case of A, it is concentrated over a large area. They will also attract the electrons, but less than that of the smaller cation C. Okay, so smaller the size of cation, smaller the cation size, more is the polarizing power. Polarizing power increases. And what about covalent character? CC is covalent character. I have written here, covalent character. So if the polarizing power increases, the covalent character also increases. Okay, so smaller the cation size, more is the polarizing power. Covalent character is also more. Okay, so this is one factor. Okay, for example, if I have lithium ion, sodium ion, potassium ion, rubidium ion. They are all from the first group, and we know lithium, sodium, potassium, rubidium. Okay, so as you're coming down, what happens to the size? Size is becoming lesser. So which atom is smaller comparatively? Lithium. So for lithium ion, the polarizing power will be more and covalent character will be more. So this is how we arrange. Okay. Similarly, we take one more example for beryllium, magnesium, calcium, strontium. They are all from the second group. Beryllium, magnesium, calcium, strontium. So as you're coming down, what happens to the size? Size is increasing. So polarizing power becomes lesser. So beryllium is smaller in size. So that will have more polarizing power than the rest of it. Okay. So if the size is small, polarizing power more, covalent character is more. Right? This is the first factor. Okay. The second factor is the size of the charge of the cation. Charge of cation. If the charge is more, will it attract the electrons more strongly? Yes, it will attract the electrons of the, if the charge is more, it will attract the electrons of the anion more strongly. So what happens to the polarizing power? Increases. So covalent character increases. Okay. So for example, if I have sodium, magnesium, aluminium. So where is the charge more? Charge is more for aluminium. So that will have a more polarizing power than magnesium. Magnesium will have more polarizing power than sodium. Okay. Similarly, if I have potassium ion and calcium ion. Here, the size is, they are in the same period, so size doesn't differ much. Okay, so we have to look at the charge. So who has a greater charge? Calcium. So if the charge is more, polarizing power is more. Covalent character is more. So it will attract the electron more strongly than potassium. Right? I hope till here it is clear. So more polarizing power means the polarizing power is more. That means it will distort the electron cloud of the anion more. So covalent character increases. Okay, so these are the two factors. Okay. Now we move on to our third factor. The third factor for the cation is pseudo-noble gas configuration, PNGC. Okay, now what is this? Pseudo-noble gas configuration, like noble gas, configuration like the noble gas. For example, noble gas neon has a configuration of 2s2, 2p6. Argon has 3s2, 3p6. Krypton has 4s2, 4p6. They have ns2 and p6. This is for noble gas. I'm talking about the outer valence shell configuration. Okay, so this is for noble gas. Now, for pseudo-noble gas configuration, they will have these cations have configuration like the noble gas. They will have a configuration like this, ns2, np6, nd10. It's like fully filled, right? All the orbitals that are there is fully filled. So this type of configuration is called as pseudo-noble gas configuration. Okay, so whichever cation has this type of configuration, more polarizing power, and the covalent character increases for these type of cations. Okay, so ns2, np6, nd10. So if you see this configuration, straight away the polarizing power is more. Okay, so 18 electrons here, right? For example, copper. The atomic number is 29, right? So argon 18. Then we have 3d10, 4s1. I'm writing for copper, not copper cation, the copper atom. Okay. So here I'm writing down the whole configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1. Okay, but if I write copper ion, copper 1 plus ion, okay, from where the electrons is lost, the electrons are lost from 4s. So this electron is lost. And we are left with what? We are left with what kind of configuration? Pseudo-noble gas configuration. So for this ion, what is the polarizing power? It is more. So the covalent character is also more. Okay, so this is for copper ion. Similarly, silver. Below copper is the silver. So what will be the configuration for silver ion? 4s2. I'm just writing down the outer configuration, okay? 4s2, because silver is below copper. So 4s2, 4p6, 4d10. And for gold, below silver. So 5s2, 5p6, 5d10. So all these three ions, the polarizing power is more and covalent character increases. Why? Because what type of configuration these ions have? Pseudo-noble gas configuration, which is ns2, np6, nd10. This is pseudo-noble gas configuration, like noble gas configuration. Okay, so Similarly, if I take the example of, so I have 3 ions here: copper ion, silver ion, gold ion. Polarizing power is more, covalent character is more. Okay, so this is very, very important. Then I have another example, zinc. Zinc, the atomic number is 30. So I have 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2. Okay. Now, if zinc is losing 2 electrons, zinc ion, from where the electrons are lost: 1s2, 2s2, 2p6, 3s2, 3p6, 4d10. For zinc ion, from where the electrons are lost? The electrons are lost from 4s2. So we don't write that because it is zinc ion. Now, what kind of configuration do we have? The zinc ion: pseudo noble gas configuration, right? So zinc cation has pseudo noble zinc cation, okay? Pseudo noble gas configuration. Polarizing power is more, so the covalent character is more. Similarly, below zinc, we have cadmium, we have mercury. All of them have more covalent character because of pseudo noble gas configuration. Polarizing power is more. So for covalent character for cation, check the size. If it's smaller, polarizing power is more. Check the charge. Charge is more, covalent character is more. Also check copper ion. Directly you can write for copper ion, silver ion, gold ion, zinc ion, cadmium ion, and mercury ion. So check for the size, charge, and these 6 elements causes polarizing power, more polarizing power. Okay, so this was for the cation. Okay, so these 6 elements, ions, you can just memorize and keep, so it becomes easy. You don't have to write down all the configuration all over again. So just memorize these ions. Okay, copper ion, silver ion, gold ion, zinc ion, cadmium ion, and mercury. Okay, so this was for the cation. Okay, the polarizing power of the cation. So next is for the anion. Which anion gets more polarized? Okay, first is the size. Now, if I have 2 anions, okay, so this is one anion, and this is another anion, anion A, anion B. If it's bigger anion, okay, the nucleus cannot hold the electrons together like the smaller anion. So, if the size of anion increases, what happens to polarization? Polarization increases. It's not polarizing power. For anion, it's polarizing. How the electron cloud gets distorted, that's polarization. So polarization is for anion. I'm denoting it with P. Okay, so polarization increases, covalent character increases. So as the size increases, more distortion takes place, distortion of the electron cloud or deformation of electron cloud takes place, more polarization increases and covalent character increases. Okay. Now the second factor is the charge. Charge on the anion. For example, an anion has -1 charge and -2 charge. Okay, so whoever has more charge is more, polarization is more. The electron cloud of that anion gets deformed more and covalent character increases. So more charge, more chances, more polarization. And covalent character increases. So this was about the anion. So for anion, larger the size, more is the polarization, more is the covalent character. And charge, more the charge, more is the polarization, more is the covalent character. Okay, I hope till here it is clear. We will be solving some questions. It will be more clear then. Okay. Okay, students, let's summarize the Fajans rule. Okay, until now. So, Fajans rule summary. Rule summary. Okay, so it is imparting covalent nature to covalent character to ionic compounds. So how much of covalent character is there in an ionic compound? And it's not percentage or anything, it's just comparison of some compounds, that's it. So covalent character depends upon two factors. One is polarizing power of cation, polarizing power of cation, and for anion it is polarization. Polarization spelling. Polarization, I denote it with P, right? Of anion. Right. So covalent, how much of covalent character is there in an ionic bond depends upon these two factors. Depends upon the cation as well as the anion. For cation, it's the polarizing power. How much it can deform the electron cloud. Polarization, how much the electron cloud gets deformed for the anion, right? So for cation, it is cation size. As the size is smaller, for smaller cations, more is the polarizing power. So as the cation size decreases, polarizing power increases. What happens to the covalent character? Covalent character increases, right? Similarly, we have charge. We are talking about cations here. Cation, charge. As the charge increases, what happens to the polarizing power? Increases. And covalent character increases, right? Then also for cation, we have one more factor, which is called as pseudo noble gas configuration. If it is more, if it is there, polarizing power, if any cation has this type of a configuration, pseudo noble gas configuration, the pseudo noble gas configuration is NS2, NP6, ND10. NS2, NP6, ND10. This is the pseudo noble gas configuration. If the cation has that, polarizing power increases, covalent character increases. And we discussed 6 cations that has pseudo noble gas configuration, that are copper ion, right, with another color, copper ion, silver ion, gold ion. Then I have zinc ion, zinc cation ion, cadmium ion, and mercury ion. So all of these ions have, all of these cations have pseudo noble gas configuration. So for them, polarizing power is more and the covalent character increases. So this was for cation. We also discussed for anions. For anions, size. So I'll write anion size. So it's not. So anion size. So here, this is for anion. Anion size increases. What happens to the polarization? Polarization is more. Covalent character is more. Charge. If charge is more, what about the polarization? Polarization is more. Covalent character is more. So this was the summary of Fajans rule. Okay. How much of covalent character is there in the ionic bond? Depends upon the polarizing power of cation and the polarization of anion. Okay, I hope this is clear. Now we'll practice some questions. Okay. We'll apply these rules and practice some questions. Okay. So question number 1. You have to tell the covalent character, and we know that it is not the measuring the percentage or anything, it's the comparison of different ionic compounds, right? So you have to tell how much of or which of them have higher covalent character. Which of the compounds have, or arrange the following compounds in increasing or decreasing order of covalent character. Okay, so first one is, if I have lithium chloride, sodium chloride, potassium chloride, and rubidium chloride. Okay. So the cation is, the anion is the same, all of them chlorine, chloride ions are there, right? So we go with the cations. So cation is in group 1, lithium, sodium, potassium, rubidium. All of them have charge 1, 1 plus, same charge. So we have to look at the size. As you're coming down, what is happening to the size? Size increases down the group. Size increases down the group, right? So for cations, we discussed smaller the size, more is the polarizing power. So lithium has the smallest size, right? So lithium has more polarizing power than sodium. Sodium has more than potassium and then rubidium. So smaller the size, more is the polarizing power and more is the covalent character. Okay. Second example, we have beryllium chloride, magnesium chloride, calcium chloride. For all of them, the anion is the same, chloride is the same. So we go with the cation. All of them have the same charge. Beryllium has, magnesium has, calcium has 2 plus positive charge, right? And they are in group 2, beryllium, magnesium, calcium. As you're coming down, what happens to the size? As you're coming down, size increases, right? So who has the smallest size? Beryllium. If the size is small, more is the polarizing power. Size is small, polarizing power is more, covalent character is more, right? So beryllium has the higher polarizing power. So that means beryllium chloride is more covalent than magnesium chloride, which is more covalent than calcium chloride. So calcium chloride will be more ionic. Less covalent, so more ionic, right? So We have the third example, sodium chloride, sodium bromide, sodium iodide. Now the anions have changed, right? The cation is the same. Sodium is the same. Now we go with the anion. Let's look at the charge first. -1, -1, -1. So charge is the same. So we look at the size. So chlorine, bromine, iodine. As you're coming down, the size is more. Who has the least smaller size? Chlorine has a smaller size. Who has the higher size? Iodine has a bigger size. For anions, size more. As the size increases, what happens to the polarization? Polarization increases. Covalent character increases. For anions, in terms of size, it's different. Size is more, that anion will have more polarization. So sodium iodide will be more covalent because we are comparing for anion. I hope it is clear till here. Right? Now, let's look at the applications of this Fajans rule, and then we will practice some more examples. Now, applications. If any ionic compound is more covalent, has more covalent character. If any ionic compound has more covalent character, CC, okay, then if covalent character, CC, I said it is for covalent character, just a short form. If the covalent character increases, what about the solubility? Solubility will be very less because we know that ionic compounds are more soluble in water, covalent compounds are less soluble. They will be soluble, but the solubility will be less. Okay. So these type of questions are very important for the competitive exam. Like they give 2 or 3 ionic compounds and they tell which compound is more soluble, which is less soluble. So you have to look at the covalent character. If the covalent character is more, that means the solubility of that compound will be less because it is behaving more like it's having a more covalent character. And you know, covalent compounds are less soluble compared to ionic compound. Okay. Again, you know that covalent compounds have weaker bonds compared to, so covalent bonds are, or covalent compounds have, or covalent bonds are weaker compared to ionic bond. They have less melting and boiling point, right? I'm talking about covalent compounds. Why? Because if the covalent character is more, those compounds will have less melting and boiling points. Because the covalent compounds they are behaving like that. So covalent compounds have less melting and boiling point. Okay. For what kind of compounds? Covalent compounds, yes, you know, but also covalent, if the covalent character is more, those compounds have lesser melting and boiling points. Okay. And those kind of compounds whose covalent character is more will be imparting more color. So that means they have color imparting nature. They will be more darker in color. Where these applications, where do we use this? We will just practice some questions. We will use these informations. Okay. So the ionic compound whose covalent character is more will be less soluble. They will have less melting and boiling point, and they will have color imparting nature. That means they are more darker in color. Okay. So let's use these applications. Okay. For example, if I ask a question, which of the following have higher melting point? Okay. So the first one, beryllium fluoride, magnesium fluoride. Both are ionic. We cannot directly say, so we need to check the covalent character. So both the anion is the same. So we check with the cation. For cation, the charge is the same. So we look with the size. We go with the size. Beryllium, magnesium. So as you're coming down, the size is becoming more. So beryllium is more. Beryllium, for beryllium, because the size is small, the polarizing power is more. So for beryllium, because the size is small, polarizing power is more. So that means beryllium fluoride is more covalent than magnesium fluoride. Okay, so beryllium fluoride have low melting point because the covalent character is more. But this they have asked for higher melting point, right? So beryllium fluoride has low melting points. I've written down the information, but the sign was wrong. Okay. Anyhow, beryllium fluoride, it has lower melting point. The covalent character is more. But for magnesium fluoride has a higher melting point. What about the covalent character? Covalent character is lesser. So who has a higher melting point? The question is who has higher melting point? So who has higher melting point? Magnesium fluoride. Okay, let's practice one more question. They have asked for who has a higher melting point. Okay, calcium chloride, calcium bromide. The cation is the same. We go with the anion. Both have -1 charge. Chlorine, bromine. As you're coming down, what is happening to the size? Here also, who has higher melting point? Okay, who has higher melting point? So you need to check who has higher melting point. Okay, so chlorine and bromine, as you're coming down, the size increases. So for anion, what did we learn? If for anion, size is more, as the size increases, polarizing increases. So bromine has more polarizing, right? Polarization is more for bromine. So here, the covalent character is more. Why? Because the polarization is more, because the size of bromine is more. So what happens? Covalent character is more. If the covalent character is more, what about the melting point? Less melting point. If it has less melting point, who has the higher one? Calcium chloride. Right? Because the question is not about, they have not asked to arrange it according to covalent character. They have asked you to arrange according to the melting point. Hope this is clear. So I'll just which compound has higher melting point. Okay. So I hope this is clear. The reasons I have written it down. Okay. Now the third one, sodium chloride, copper chloride. So anion is the same for both of them. So we go with cation, sodium and copper. Here the charge of sodium is 1 plus 1. Copper also is plus 1. Okay, with the formula you can find out that the copper has a valency of 1, or the copper charge is plus 1. Now, we just studied for copper cation. Copper cation. What kind of configuration? Pseudo noble gas configuration for copper. So directly we can say polarizing power is more. So if the polarizing power is more, covalent character is more. What about the melting point? Melting point is less. So who has more melting point comparatively? Sodium chloride. Okay, the reason I have written it down. Next one, potassium chloride, silver chloride. So whenever these type of ions, those who have pseudo noble gas configuration, please memorize the 6 ions and keep so that it's easy for you to write. So here the anion is the same, chlorine. So we go with cation, potassium ion, silver ion, both have charge +1. Okay, now for silver ion, we learned silver ion has pseudo noble gas configuration. Polarizing power is more. So the covalent character is more. What about the melting point? Is lesser. So comparatively, who has a higher melting point? Potassium chloride. Okay, so I hope this is clear. Now, similarly, another application we talked about solubility. Those compounds that have more covalent character are less soluble. So, which is more soluble? Which is more soluble? FeOH3, FeOH2. So if the covalent character is more, solubility is less. Right. So here, the anion is the same. So we go with the cation. Here the cation, the charge is 3 plus. Here the charge is 2 plus. Okay. So we learned that for cation, if the charge is more, polarizing power is more. So who has more polarizing power here? Charge is more here, right? In this case, Fe3 plus. Polarizing power is more, covalent character is more. So if the covalent character is more, what about the solubility? Solubility is less. So FeOH3 is less soluble than FeOH2. Okay. So another question for solubility. Silver oxide, silver sulfide. The cation is the same. So we go with anion, oxygen and sulfur. Both have a charge -2. Oxygen, sulfur. As you're coming down, what is happening? Size is increasing. Size increases as you're coming down, right? So size increases as you're coming down. So who is bigger in size? Sulfur. If the anion is larger, polarizing is more. Covalent character is more. So in this case, for sulfur, it has more size. As you're coming down, the size is more. So sulfur has a larger size. So polarizing is more. Covalent character is more. So less solubility. Silver oxide has more solubility. So when the covalent character is more, melting point is less, solubility is less. And what about the color imparting nature is more that we will be discussing now. Color imparting nature is more when it is having more covalent character. For example, if I have the following compounds. Okay, so this is just a summary of the application. Okay, so we discussed about melting point now. We did some questions about solubility. Now, let's do some questions on color imparting nature. Suppose I have some compounds, silver fluoride, silver chloride, silver bromide, and silver iodide. Which compound is darker? Which one is lighter? Okay, so question is, which is darker? Which of these elements or which of these compounds, sorry, is darker? Okay, so the cation is the same silver. So we go with what? We go with anion. All anions have the same charge, -1. So we go with the size, fluorine, chlorine, bromine, iodine. Okay, now as you're coming down, what is happening to the size? Size is increasing, right? So that means iodine has the largest size. So as size increases for anion, as the size is more, polarization increases, covalent character also increases. So that means silver iodide has most covalent. So this one, so silver iodide has the most covalent character. If it is more covalent, that means it will be more darker. Okay, this is the darkest. This compound is more darkest because the covalent character is more, because of the large size of iodine. And it is actually seen that silver iodide is dark yellow. The next the next more covalent one is silver bromide, right? So that will be yellow. Silver chloride is white. So see, you can see the color is becoming lighter. Silver fluoride is colorless. So as you're coming towards the left, it is becoming, or when you come from iodide to bromide, bromide to chloride, chloride to fluoride, see the color is becoming lighter. Silver chloride is the darkest, silver iodide is the darkest, silver fluoride is the lightest in color because it has less covalent character. Right? So this is how you decide. Let's practice one more example. Same question. You have to tell which compound is the darkest. Okay. So whichever has more covalent character, that will be the darkest. Lead chloride, lead iodide. Okay. Now we have the cation is the same. So we go with the anion. Both of them have -1 charge. So chlorine, iodine. As you're coming down, the size is more. So more covalent character. So iodine will have is the bigger one. So it will have more covalent character. More covalent character. Covalent character is more because iodine size is bigger. So if the covalent character is more darker. It is seen that lead iodide is dark yellow in color. Okay, so you just have to say that it is darker. So I'm just telling you for your information, it is dark yellow in color and lead chloride is white in color. Okay, I hope this is clear till now. Okay, so let's practice one more question. Suppose I have given you two compounds, tin chloride, SnCl2 and SnCl4. Okay, tin is having different valencies here. Here the valency of tin is, charge of tin is 2 plus. Here it is 4 plus because okay, so here tin 2 plus, the charge here, the charge of tin is 4 plus. Okay, the anion is the same. Now, if the charge for cation, greater the charge, more the charge. If the charge is more, what about the polarizing power is more? Covalent character is more. Okay, so my question is, among them, why SnCl4 is a volatile liquid? Volatile means something that has a lower boiling point and okay, melting point. Volatile liquid, while SnCl2 is a solid. This is the question. Now we already decided, we already understood that SnCl4, okay, has the higher polarizing power because of the higher charge of Sn4 plus. That is why the covalent character is more. If the covalent character is more, definitely it will have lower melting and boiling point. Okay, it has more of covalent character, more covalent character. So that is why it is a volatile liquid. Usually, you know, covalent compounds exist mostly as liquid and gases, very less amount as solid. Okay. And what about SnCl2? Here the charge is less, so less covalent character, and that is why it exists as a solid. Okay. So covalent character is there, but the covalent character is less. Okay. So students, today we studied about the Fajans rule, which is the covalent character in ionic bonds. Okay. So we also studied the criteria to decide which ionic compound has more covalent character, and also some applications. So we practice some questions, more questions we will practice when we do the past paper questions, practice questions. Okay. So students, that's all for today. Thank you. Have a great day.